go. It's all yours. Go ahead.
Apologies in advance. We have lots of covers, so I'm going to move very quickly. Good evening, everyone. My name is Gene Levant. I'll be going over my project of Delta V optimized interplanetary trajectories from Earth to Uranus. Some background on my project. In 2023, the National Academies of Sciences, Engineering, and Medicine identified for NASA that a mission to Uranus was our highest priority flagship mission, since the last mission to Uranus was Voyager 2 back in 1986. For this mission, they suggested to send to Uranus both an orbiter and a probe, with optimal launch times in 2031 and 2032, and then less ideal opportunities in 32 to 38, due to opportunities with Jupiter in 31 and 32, and then uses of the inner planets in the remainder of the window. To solve this work on this project, my goal is to optimize the delta V requirement of the Uranus orbiter to enter Uranus's orbit from Earth deployment. We'll be assuming the use of an inertial upper stage to decrease the required delta V of the spacecraft. We're also going to be requiring the use of multiple gravity assists with no deep space maneuvers, just the velocity changes at each of the flyby periapses. We'll also be using the solutions of Lambert's problem to calculate the departure and arrival velocities for each leg of the trajectory. However, from Mercury to Jupiter, there's hundreds, if not thousands, of ways to get out to Uranus. So we need a quick way to search through all the parameters of departure and arrival dates, number of gravity assists, the order of the gravity assists, as well as the time in between each of the gravity assists. So rather than use brute force and look at every single permutation, I decided to employ a genetic algorithm. This algorithm is used to explore problem spaces of very complex nonlinear problems. However, the genetic algorithm often produces optimal solutions near the global minimum, but not the global minimum. So for my methodology, after a route and timeline was initially identified, I fixed the route and then try and optimize the delta V based off the timelines for that route. Performed that about 5 times to try and get the best opportunity that I could. And once that was minimized to the best of my ability, I locked that route into place so that the genetic algorithm would not find that opportunity again. Just a little background on genetic algorithm. So you try to optimize a series of variables or genes such that you minimize the cost of a fitness function. Each series of genes build up a chromosome, and then a population of chromosomes are what are being evaluated at every single time. So you provide a lower and upper bounds for each gene. You generate a population of randomized chromosomes, and then for each member of the population, it's, like I said, explores a fitness function, and then the elite, or I guess you perform pseudo-evolution to find the optimal solution that minimizes your cost function. So for the use of the genetic algorithm in my project, without considering deep space maneuvers, the total delta V is just a function of time. Your departure dates, time between legs, and time to your final planet. So using the solutions to Lambert's problem, you can see the delta V equation that I use, which is basically the delta V and the difference of the energies of inbound and outbound trajectories. So the cost function that I'm trying to minimize is a sum of this delta V as well as penalties that I would apply to poor trajectories. And these would be low energy arrivals, which would be non-hyperbolic on arrival, usually to the first planet, as well as low passes that would enter the atmosphere or crash into the center of the planet. And then finally, down at the bottom is an example of a chromosome that I would use to run my cost function. So departure dates, number of flybys, the planets in that order, the corresponding times, and then the time of flight to the final planet. And the 2 last symbols are actually angles of the B-plane in case of a resonance orbit during the trajectory. So to validate and verify my work, I want to try and recreate an existing mission. So I decided to try and recreate Galileo, NASA's mission to Jupiter. So I'm focusing on recreating the gravity assist and interplanetary trajectory design, and not focusing on the secondary asteroid close approaches. So the results of my algorithm should produce comparable results in terms of dates of departure, close approaches, and arrival, the gravity assist altitudes and closest approaches, as well as the total delta V requirement by the spacecraft from deployment to Jovian capture. So just an overview very quickly. Launched in 1989 from the space shuttle Atlantis. Had an inertial upper stage with an injection energy of 17 kilometers squared per second squared. Performed 3 gravity assists, 1 of Venus, 2 of Earth. During each of the legs, performed a flyby of the asteroids Gaspara and Ida, respectively, and required a total delta V budget of 815 meters per second, just shy of 200 for total trajectory corrections, and 630 for the capture at Jupiter. So the parameters I gave my genetic algorithm, I gave it a 2-month launch window from October 1st of 1989 to November 30th. I modeled the same inertial upper stage, same gravity assist order, same number of gravity assists, and I initially tried a very large spread of times between the legs, but I wasn't able to converge on a good solution, so I shortened it to plus or minus 10 to 20 days for each of the legs relative to the real flight data. And these are actually the results of that genetic algorithm. So you can see my dates are spread from 10 days to about, or 3 days to about a month apart, ranging from initial departure to arrival at Jupiter. The injection energy is about 1 kilometer squared per second squared in difference from the real data. And although Galileo did not perform any maneuvers during its Venus and Earth approaches, I have very minute maneuvers, millimeters and to the tens of meters level. Then actually my arrival at Jupiter is less expensive delta V-wise than the arrival of Galileo. And then far right column you can see the periaps altitudes for each of the flybys and departure and arrival. So here's a 2D projection of my genetic algorithm projection. So the red line is the Galileo flight data, and the black line, which is a little harder to see, thankfully, is my genetic algorithm recreation of the Galileo program. So you can see basically in the residence orbit, which is the larger outbound trajectory and the inner solar system trajectory, are my greatest deviations. But the Earth to Venus to Earth and then out to Jupiter, very comparable in data. Here's a couple more just to verify that my models are good, are the magnitude of the distance from the sun for each trajectory, as well as the difference in their magnitudes from launch date to arrival. Now, moving on to the constraints I apply to my interplanetary trajectory to Uranus. Following the ideal timelines, I wanted to give it a launch window of 5 years from January 1st of 2030 to December 31st of 2034. I'm modeling a slightly improved inertial upper stage at 18 kilometers squared per second squared, and I allowed eligible flybys of Mercury through Jupiter. I'm not including Saturn because Saturn's in an non-ideal position and would cause very wild trajectories and fling you in towards the sun. I allowed anywhere from 3 to 10 gravity assists, time between legs 50 to 2,000 days, and then the last leg 100 to 6,000 days. And then I wanted to try and get a wide range of unique ideas or trajectories, so I ran the algorithm until I had 60 unique solutions. So here are the top 10 solutions identified by my genetic algorithm. Starting with the top one, which I'll go over more in the next couple slides, is an Earth, Venus, Earth, Jupiter, Uranus approach, requiring about 2.5 kilometers per second of delta V, leaving in the ideal window identified by the paper from April 28th to 2031, but arrival of 21 years later in 2052. So this is a breakdown of that trajectory. We can see it actually underperforms in terms of the injection energy required or provided by the inertial upper stage. Near zero impulse required at Venus. However, hefty delta V corrections at Earth and Jupiter, while their actual capture at Uranus is the lowest of the performance delta V requirements. And now here's the corresponding projection for that trajectory. A black line, again, is the result of the genetic algorithm, and then I tried color coding the plans to the best of my ability. In conclusion, although there are thousands of trajectories to get a spacecraft to Uranus, the algorithm employed for this project was able to identify 60 unique preliminary trajectories. While solutions to the Lambert's problem are great for two-body problems and solutions, trajectories to the outer solar system can be greatly impacted by the gravitational forces of the gas giants. It's effectively Jupiter's playground out there. So most likely, unlike my project, a deep space maneuver will need to be performed to counteract those perturbations. However, the goal of this research was mainly to serve as a starting point for future discussion and higher fidelity research. Of the trajectories identified, one thing I actually thought was pretty surprising, the value of the provided injection energy greatly shifted the delta V requirements. So for the example I showed you, the total injection energy actually wasn't consumed, whereas others, the greatest performance or requirement of delta V was from the initial injection from Earth into the trajectory. In the future, I wanted to further develop this research, or further development of this research should consider deep space maneuvers as a part of the genetic algorithm fitness function, provide a greater baseline for the possible trajectories out to Uranus. After including deep space maneuvers, the next step in the research should be to include a tuning algorithm to create a smooth, continuous trajectory that accounts for the spheres of influence of the planets that you fly by. Or another would be to improve the process of Lambert's problem, so you can study the effects of gravitational perturbations in the incorporated solutions. And additionally, more work can be done in calculating other possible routes. I was just limited to identifying 60 trajectories due to the highly intense computational nature of the project. Some of the lessons learned I brought home from this was, while more interplanetary trajectories were what I was hoping for, I was severely limited by the computer I was using, even though I just made my computer about 6 months ago. For the 60 trajectories, it took over 12 hours and 15 gigabytes of RAM to compute all 60 of those trajectories. For each use of the genetic algorithm, actually concluded to a different solution. So sometimes I have to run 2 or 3 times, at least initially, for the Galileo validation and verification to make sure I actually got a good solution. And additionally, one of the other interesting takeaways I had was that this genetic algorithm tended to prioritize studying the minimum number of gravity assists for its results, likely due to the unrealistic trajectories that would have occurred if you had 7 initially without anything to compare it against. And that concludes my presentation. Are there any questions?
All right. Any questions for Gene? Yeah.
Thanks. Those 10 trajectories you showed, or those 10 candidates you showed, I guess was those based on like delta V, or I guess what was the main choice in choosing those 10?
Yeah, so I just built this list based off of the 10 lowest delta V requirements. So as you can see, it ranged from 2.5. Actually, the 60th trajectory was about 12 kilometers per second of delta V, but ranging anywhere from 2 gravity assists actually up to 7 in my list of 60. And so yeah, just listed it by delta V. That's what I was trying to optimize for this project.
Cool, thank you.
This table, by the way, is pretty depressing, isn't it? Yeah, I will probably be not working by then. But
Yeah, I thought the second from the bottom was pretty interesting because it's less than 15 years actually to get out to Uranus.
That does look pretty promising. This is arriving. Rendezvousing with Uranus, not flyby, right?
Yeah. So this would be the captures included. So if we actually look at the next slide, the Uranus arrival, that would be the delta V required for a minimum energy capture of an eccentricity of 0.998. So just the bare minimum to get captured kind of would replicate what Galileo did at its capture of Jupiter.
Yeah, so can you go back? For the 4 kilometer per second delta V, I just don't remember the actual amount of the fuel required for this. Is that practically doable?
It would depend on how much you're willing to perform. I know with Galileo, they were very concerned about trajectory correction maneuvers, and a lot of the routes were actually not possible because it left them with 100 meters per second for trajectory corrections and pathfinder changes. And so it would effectively depend. If you can actually have a very high performance upper stage, some of these trajectories actually might be more viable. So actually the second option, the Earth, Mars, Jupiter, Uranus option, its greatest cost is actually the deployment into its orbit. And so if you are able to get a higher energy inertial stage, this would actually be a very cost-effective way of getting to Uranus that would only cost you less than a kilometer per second, modeling in the two-body problem sense.
Can you go back to the slide 14 again? All right, so these are all great options, but I personally will not select anything that has V in it. You want to take a guess on why? Or actually, many engineers will not like V in it.
Just the heat getting close to?
Exactly. So if you're trying to do a flyby of Venus, Venus is obviously closer to the sun than Earth and the others, right? So it's going to require different kinds of the thermal requirements. So it has to satisfy different thermal requirements, and that sounds easy, but it actually makes your spacecraft a lot more costly and so on. So sometimes you do have to balance the delta V versus the time versus the cost versus the mass and so on. So just FYI, but this is a pretty good deal.
And I thought it was really interesting when I actually had plotted, which I unfortunately didn't include in the presentation, was my quadruple Earth, Jupiter, Uranus trajectory. Basically, it would rotate the orbit by about 10, 15 degrees for the 3 passes, then shoot out to Jupiter, and then would go out to Uranus.
Yeah, 33 years. Huh?
Yeah, that one was pretty hefty. But yeah, so these are just the top 10 of the 60 I collected, and so if I were to run it again, I'd probably get a different list of 60 almost.
So I have one question. What if you consider something like Starship?
In what sense?
It's going to produce a lot of delta V, right? Mm-hmm. So I don't exactly know how much kilometer per second you can produce, but if you, like you're going to do maybe in the future, if you do include the deep space maneuvers, it could make some of these, cases to be much shorter, right?
Yeah, so, or actually even delta V less intensive as well. There were some papers that were identifying that the deep space maneuvers actually simplified the delta V requirements for some of these deep space maneuvers. For Cassini, for example, was one of those examples.
Yeah, and right now, one thing I can tell you is that there are a lot of scientists and engineers wanting to arrive at Uranus in early 50s. Okay.
There's quite a few of those on there, actually.
Yeah, it all depends on many things, funding and all that, but that's the current hope. So. Anyway, thank you.
Of course.
Yeah.
Are there any questions on mine? I didn't actually see. Going once?
All right, let's move on. Okay, so who's next? Let me see.